Good morning. Morning. How is everyone this morning? Are you sleepy? Wonderful. Have you had a fun 2 weeks? And one case 1 week. Do you want to come back? Okay, there's lots of opportunities for you to come back. We are certainly delighted to have you here today. I'm Marie Westfall with ORAU, and the first thing we're going to do is do what we always do at ORAU, is we're going to give you a safety message so you know all the safety procedures if anything happens, which we don't expect it to, but just in case.
In the unlikely event of an emergency requiring the evacuation of this facility, those of you sitting in the front of the auditorium should exit immediately via the doors on the left and right sides of the stage. Those of you in the back should evacuate via the rear doors. Those on the left side should exit via the glass lobby doors on the right. These are the doors through which you probably entered. Those on the right side should continue into the lobby and straight ahead to the broad glass enclosed corridor. There, you may exit the building either to the left or right. Should one or more of these exit ways be blocked by smoke or fire, please leave via the nearest alternate route. Restrooms are located off the corridor to the left of the lobby. Water fountains are located between the restrooms. Vending machines are located at the end of the hall that parallels the auditorium wall on your right.
All right, so now you know how to get out of this auditorium. We hope you will stay for a little bit. We're going to begin this morning with Dr. Jim Vosberg. Dr. Vosberg is the director of the Oak Ridge Institute for Science and Education here at ORAU. And so, Dr. Vosberg.
Thanks, Marie. Good morning to everyone. So I normally do these very informally, but I understand they're live streaming this, so I've got to go on script this morning. But I did want to say you all look very nice, all of you students. Ties, dressed up very well. Your parents should be very proud. So welcome. Hope everything went well this week. Hope you had a good time. I'm really happy to welcome you to the final presentations and recognition ceremony for the Oak Ridge Science Academy and the ARC ORNL High School Summer Math Science Technology Institute. That's a mouthful. I'd like to take the opportunity to recognize the participating students, teachers, and welcome their families, mentors, and officials of ARC. We really appreciate the value in our partnerships with ARC and obviously Oak Ridge National Laboratory, who we work very closely with to provide these opportunities for the students and the teachers also. Students and teachers, you represent the 29th year for the Summer Institute and the 10th year for the Middle School Science Academy. We have common goals for students and teachers, basically to motivate you to stay in STEM professions. We're looking for STEM people at our national laboratories, so once you get through college, that might be an opportunity for you. Keep that in mind. So that's a common goal for the program. Our goal for the teachers is basically to expand their knowledge in the science fields and actually take it back and apply them back in your classroom. At this time, I want to welcome Mr. Tim Thomas, Appalachian Regional Commission Federal Co-Chair. Tim was sworn in as the Appalachian Regional Commissioner, the 12th Federal Co-Chair, on April 3rd this year. As Federal Co-Chair, Tim works directly with ARC's 13 member governors, their state alternates, and program managers. Tim has more than 20 years experience in public infrastructure, workforce training, which is we're heavily involved in, and regulatory issues. He was previously the Director of External and Regulatory Affairs for Swift and Staley. Tim has a bachelor's degree from Murray State, Kentucky, and a law degree from the University of Louisville. Please join me in welcoming Mr. Tim Thomas to the stage. Tim.
Good morning. It's great to be here. I can assure you of that so much. My office is in Washington, D.C., but when I get to be out in the region amongst the people of Appalachia and see what exciting things they're doing, it really makes my day. And the Appalachian Regional Commission, we are actually an economic development entity chartered by Congress in the 1960s as a partnership between the federal and state governments, the 13 states that touch upon the Appalachian region. And our role as an economic development entity is why we are here with you today and why the ARC has been a sponsor of this program since the year 2000. Each year, ARC collaborates with the Oak Ridge National Laboratory to bring high school and middle school students to our summer STEM programs for students and teachers from the Appalachian region. Since 2000, when ARC became a partner in this effort, over 1,100 participants have successfully graduated from the program. Why do we do this? Because we are investing in the future of Appalachia, and you are part of that future. And we believe that helping today's students become interested in future studies and careers in science, technology, and math will help the region grow and thrive in the years to come, creating more opportunities for all of us. And the journey does not end here today. If you are a middle school participant, you can come back as a high school student. If you are a high school student, the lab provides internship opportunities for college students. And if perhaps you are interested in working at ORNL in the future, there are various career pathways that you are able to enter into as an adult. For the teachers in the audience, please share the knowledge you have obtained over the past 2 weeks with other teachers in your school system. Today's events would not be possible if it weren't for the hard work of all of the participants and teachers. You have not only spent time working on some really interesting and exciting STEM-related projects, but I also hope you have made a few friends from other parts of the Appalachian region during your time in this program. And I hope you are able to keep in touch with those friends in the future, remembering your days at Oak Ridge together. And I would note that it is a lot easier to keep in touch with the friends you made at summer camp today than when I was your age. You have social media and text and emails, and when I was your age, it was pretty much you wrote a letter or you made a phone call. And I was not allowed to make too many long-distance phone calls, but I wonder how many of you even know what a long-distance phone call is. Back in the day, they were fairly expensive. But we actually do rely on all of you to keep this program running. Please spread the word about the program to your parents, your teachers, your friends, and your community. Teachers, we count on you to recruit students and other teachers for next year's program. And to parents, thank you for entrusting your children to us. And I would also like to extend thanks to the staff of ORNL and ORAU, especially a special thanks to Jennifer, Marie, and Pi, and to the mentors for all of your work to make this program a success. On behalf of the Appalachian Regional Commission, congratulations on your hard work and on your dedication to this program. We are looking forward to what the future holds for all of you. And thank you for allowing me the privilege of speaking to you today. Thank you for having us.
Thanks, Tim. Okay, at this time I'd like to introduce David Kyne from Oak Ridge National Laboratory. He is a communication director. In his job as a communication director, David is responsible for internal and external communications, community relations, protocol visits with ORNL. Mr. Kyne holds a bachelor's degree in journalism from the Honors College at Ohio University. Please join me in welcoming David Kyne.
Hi, everybody. I hope you had a good camp, good time. Yes, nods. I'm amazed that you're awake at this hour. I have a 12-year-old rising 7th grader, and I have a 18-year-old who just graduated from high school and is going to go study mechanical engineering. And I'm really glad to see so many students here and so many teachers every year. It's really important to Oak Ridge National Laboratory that we have folks like you that are interested in science, that are interested in technology, and that are going to pursue that while you're students and hopefully into college and hopefully beyond, and maybe you'll come work for us someday. Oak Ridge is a really cool place, and I want to talk to you briefly about where you've been and why you're here and what's next. The laboratory kind of illustrates how science works. You know, in the 1930s, scientists were figuring out how the world works. They were figuring out the periodic table. They were figuring out atoms. When I talk about an atom, does any image come to mind? Maybe like a proton and a neutron and the little bands around it, some heads are nodding. In the 1930s, that's not, people didn't know that. They didn't confirm the neutron until 1932. And scientists were working on physics and working on chemistry and understanding the elements. And in 1938 and 39, some scientists in Germany threw a neutron at a uranium atom, and it split in half, and it released a bunch of energy. And that was unexpected. Typically, when you split an element, it splits into sort of two chunks, and one's a lot bigger than another, like if you're chipping off a rock and you get a little shard of a rock. But it split just about evenly in two and released all this energy, and the chemists in Germany that did this, Otto Hahn and Fritz Strassmann, called a colleague of theirs, Lisa Meitner, who was in Sweden. What was happening in Germany in the 30s? Adolf Hitler was taken over. And scientists like Lisa Meitner had fled because of a Jewish heritage, because of the persecution that they saw happening. And Otto Hahn, who was a chemist, said to Lisa Meitner, who was a physicist, "What just happened here?" And she said, "Well, your result is correct." She went out, walked in the woods, sat on a rock, and thought about it. I love that this is a woman theorist who figured out fission, who confirmed fission. She goes and walks in the snow. She sits on a log with her nephew, Otto Frisch, and she says, "What if it's this way?" And they thought about it, literally just thought about it. Then they did some calculations, and they told Otto Hahn, "Your experiment is correct. We've discovered nuclear fission." And the word spread throughout the scientific community around the world. And the scientists are the ones who told the politicians, "We got to do something about this." Because whoever can control this power is going to have an inexhaustible just about source of energy, and they can also build a really big bomb. And the scientists are the ones who went to the president and said, "This is what we discovered." And the president started the Manhattan Project, and the military and American industry and scientists came together in a way they never had before, and they started the Manhattan Project to harness the atom to build a bomb. And the science was so new that they didn't know what would work the best, so they built 4 plants in Oak Ridge. They built Y-12 to try to generate uranium, the uranium isotope that was needed using electromagnets. And they built the K-25 site to do it using a series of filters that would diffuse the gas through the filters to capture uranium-235. And they built the S-50 plant to do thermal diffusion. And they built the X-10 graphite reactor to try to see if you could produce plutonium from a nuclear reactor. It was the first nuclear reactor that operated continually. less than a year before it started, the very first nuclear reactor at Chicago turned on for a few minutes and turned off, and they took it apart, and that was it. They just wanted to see if it would work, the Chicago pile. And the graphite reactor, the X-10 site, became Oak Ridge National Laboratory. And Oak Ridge National Laboratory went on to study nuclear power, to produce isotopes for medicine. If you have undergone cancer treatments, if your parents, your grandparents have been diagnosed with radiological medicine or instruments, if they've received radioisotopes to treat their cancer, that work almost certainly traces back to Oak Ridge National Laboratory. Oak Ridge National Laboratory began exploring materials to see what would work in a nuclear reactor. They began exploring the effects of radiation on living systems, came up with the safeguards, came up with the environmental regulations to protect the world from the chemicals and the radioactive materials that were doing so much good but left waste behind that need to be dealt with. Our materials now make cars. We've 3D printed a car, an SUV, a submarine, an excavator. It's just kind of crazy. We've made metal alloys that make your vehicles run better and lighter and save you gas. How many of you are driving now? Do you like things that save your gas money? Yes, heads are nodding. We have the fastest computer in the world because you need computers to take a lot of this data that exists now and to make sense of it, because you can't do it on a slide rule like they did with the first nuclear reactor. The Summit supercomputer that we just announced in June can do 200 quadrillion calculations a second. Those numbers are too big for me, so here's how I think about it. There's 7 billion people in the world. Think about what you were doing at the beginning of the school year, last September. You got in your head how long ago that was? Last September. If every person in the world started doing one calculation per second, 1 + 1 = 2, 2 + 2 = 4, 2 × 2 = 4. I won't go much beyond that because I'm just an old journalist. If every person in the world did one calculation per second, starting the beginning of the school year, right about now, everyone, if you didn't eat, you didn't sleep, you just did that 24/7. You'd finish calculating what Summit can calculate in 1 second. These supercomputers are as big as this room. And what we're doing now is trying to advance science that improves the technology that y'all use, the materials that we use to build stuff, the medicine that we use to treat disease, the energy that we use to keep the lights on, to power our industry, to help our military. The nuclear navy came out of Oak Ridge. The aircraft carriers and submarines that keep us safe. We're trying to make that better because, as Mr. Thomas said, the world's different now that he's younger than me and I'm not that old. And the world is radically different. Just in 10, 20, 30 years. China is rising. India is rising. We're in a global economy, and you are going to keep America competitive. Whoever masters the materials, whoever leads in the technology, is going to lead in economic competitiveness and in national security. The Manhattan Project was about making sure that our scientists and engineers got there first. Who's going to get to quantum computing first? Who's going to get to lightweighting materials that'll allow you to take electronics and just stick them on the wall where no one even notices them? That's what's next, and that's where I'll leave my comments. You're next. You guys are next. And your willingness to follow where your curiosity leads you, and your willingness now to discipline yourself to learn how to do science and to learn how to do development is going to dictate what happens in the future for our country and for the world. Take yourself seriously. Don't let anyone say, "Oh, you're just a kid." You're going to be grown before you know it. Can I get an amen from the parents? And you teachers, let me thank you for what you do. I know you don't get paid much. I know you got a bureaucracy wearing you out. I know you got smart alecky kids, none of these children, I'm sure. I know you got parents that are criticizing you. I know you have the pressure of standardized test scores, but thank you for being here, and thank you for teaching students, and thank you for loving those kids and giving them a place where they can learn, and sharing your knowledge and growing your own knowledge so you can be better. I'll tell you, as the spokesman for Oak Ridge National Laboratory, that your success is directly linked to our success. And whoever wins science and whoever wins technology is going to lead in the world. And the last thing I'll say to you is, we had a speaker at the lab recently, Thomas Friedman, who writes for the New York Times, kind of writes books now. He kind of does whatever he wants now. And he points out that the technology is changing the world incredibly rapidly, that the world's changing faster than we can kind of keep up. And technology is making people mean in some cases. You guys are growing up in a world where you can keep track of your friends that you meet here through social media, and you can also experience really ugly stuff through social media. Technology has an upside and a downside. And as technology allows us to reach around the world in an instant, as technology allows bad people, terrorists, to use the extreme example, to send a note to their followers on the other side of the world that says, "Go drive a van down the Tower Bridge in London and kill people." That same technology can be used to share knowledge and to share kindness and to share goodness. And why am I talking about that in this discussion? Because as you pursue your science and you pursue your technology, you guys are smart kids. And as you do what you do, Thomas Friedman said, and this was remarkable, talking to a room full of PhDs at the lab, he said, "It's never been more important to follow the golden rule. It's never been more important that we have strong communities and strong institutions of faith and civic service, that we teach one another how we're supposed to behave when our behavior can so instantly reach so many people." You guys are leaders if you're here. Be the kind of people you want people to be. Thank you for your time here. Thank you, teachers. Oak Ridge National Laboratory was thrilled to have you here, and we certainly hope that you teachers come back and that another group of students comes back. And y'all come back if you want to, if you're allowed to. That's Jim's decision. He decides all that stuff. But thank you very much, and I look forward to hearing about your work and maybe get to meet some of you afterward. But thank you very much.
Good morning. I am Kara Canario, and I am the project lead for the Middle School Summer Science Institute. And we're pretty excited that we just finished up our 10-year in this project, which is a big deal. So I want to just kind of start things off with presentations. We're going to start with the middle schoolers, but first I just want to tell you all about the amazing week we had. We honestly, I think that we may have had the easiest group of kids that we have ever had in this program. Parents, it is really hard to put a 12-year-old on an airplane to go spend a week across the country with a bunch of people you've never met. So we really appreciate your willingness to do so, because I think it's made a big difference for your kids to be here this week. So thank you, and thank you for sending us great kids. Thank you, students, for having a great week, for being enthusiastic, for being excited, and for being extremely well behaved, but also interested and willing to learn. I want to thank also, of course, the representatives from ARC, from ORNL, from everybody from ORAU who does so much work to pull this program off every year. And lastly, I just want to mention our master and resident teachers who spend a great deal of time preparing and making sure that parents feel comfortable putting their 12-year-olds on an airplane across the country to stay with teachers they don't know. So I will introduce our teachers individually as they come up with groups, but we in the middle school program do 3 research topics, and they will come up as a group and tell you what they learned this week. So we'll start off with our 3D printing group. So this is Master Teacher Brent Lee and Assistant Teacher Haley Evans and some of our kids.
Hello and welcome to the ORCU Middle School Science Academy presentation. The first group is going to be 3D printing. My name is Baker Ledford and I'm from Denmark, North Carolina.
My name is Tristan Carter and I am from Tuscaloosa, Alabama.
The first 3D printer ever made was called the stereolithography apparatus, which used liquid resin and a laser light in order to harden the resin, which gave a fine detail, but it was not very useful due to the size and time it took.
The second 3D printer was made in 1994. The reason, the way it was used was it used gypsum and resin to make the materials, but the reason it didn't work was because the materials were easy to break.
The last 3D printer is the most common 3D printer, which is the FDM, or fusion depositing model, which would use a plastic filament to melt down and model into the shape that you needed. And it is the most common and the first 3D printer to use color.
Hello, I am Samuel Ramirez, and I am from Morganton, North Carolina.
My name is George Ratliff from Waverly, Ohio. 3D printing is being used in construction. Some things that have been built with 3D printing include 6 printed buildings, a printed office building, printed Chinese villas, and those are only some of the things that have been built with 3D print.
Another way that 3D printing can be used practically is with surgery and transplants. Some cases can include having a skull implanted, a new skull printed and implanted, a new jaw printed and implanted, and then a new heart printed and implanted. Another way that it can be used practically is with clothing. You just have to scan the part of body you want clothing on, and then you make a model of it, and then you place the clothes on the model, and then you print it, and then you have clothes.
The future of 3D printing includes the following. Oh, hello, my name is Austin Grote. My name is Charlie Collins. You will be able to print airplane parts. Artificial human organs will be able to print it, and rocket parts. And you'll be able to make food in kitchens with 3D printers. More than 100,000 airplane parts will be printed. This will cause them to be lighter and more efficient. Artificial human organs would be able to be printed, which means if you were to have a heart attack, rather than your heart being replaced, it could be repaired. And NASA will be able to print rockets for further deep space exploration. Many kitchens will feature a 3D printer. This will lead for them to have delectable pizzas, biscuits, and pretzels, and etc. foods.
Hello, my name is Lauren Wood, and I'm from Hayside, Virginia.
Hi, my name is Ariella Malfero, and I'm from Accident, Maryland.
And today we will be talking to you about college paths and career opportunities in 3D printing.
We will also be showing the degrees needed to go into these fields.
Biological and scientific modeling. 3D printing can be used in biological modeling to make cells, DNA strands, etc. 3D printing can be used in scientific modeling to scale up or down larger or smaller objects to see them in greater detail.
Biomedical technology. 3D printing can be used in biomedical technology to make bones, organs, muscle tissue, etc.
Architecture modeling. In this specific example, 3D printing was used to make a smaller version of a building that would be too large to make in real life without a prototype first.
Product design. 3D printing can be used in product design to make a prototype of a product that will later be made for manufacturing.
Special effects. 3D printing is used in special effects to design and execute characters.
Animation. 3D printing can be used in animation to create a more realistic version of a character from a TV series or a video game.
Here are some examples of 3D printing designers using 3D printing in their everyday lives. 3D printing can be used for pretty much everything under the sun, from new body parts to fun video game characters.
Manufacturing. 3D printing can be used for manufacturing to create products that would be too hard to create using machining or molding.
Hi, my name is Kiera White, and I'm from Richlands, Virginia.
My name is Leah Acker, and I'm from Mountville, Alabama.
And today we'll be talking to you about the design cycle of 3D printing. Today we'll be starting off with the blue section, where we started off with finding an everyday problem and creating a solution. I made a little product that helped organize earbuds.
And I made a phone holder. After you figure out what you want to make, you sketch out your design and you add the measurements. After you add the measurements, you add it to the program you're going to use, which we use Tinkercad.
After you've built your design, you hit export and download the file, and then move on to a program called Flash Print. You load in the file, choose your machine and extruder, and then you choose the material you're going to use, temperature, and any supports you may need, after which you will download onto a flash drive.
After you download your product onto a flash drive, you put it into the printer and you start printing. If you forget to add structure or you let the plastic filament stretch too much, your product will be messed up and you'll have to start all over again.
And we would like to thank Mark McFall for letting us view his office for 3D design, for just showing us what we can do if we want 3D printing as a future hobby or career. And also Dr. Amy Elliott from Oak Ridge National Labs for telling us a brief history about 3D design and what can happen with it. And also Bentley and Haley Evans for teaching us all about 3D printing and showing us how to actually make things. I would like to introduce the drones group.
So as we have a switch out of our groups, thank you 3D group. Our drones group is led by master teacher Lauren Wilmoth and assistant teacher, resident teacher Mark Rubin.
Hello everybody, I'm Justin from a small village in New York called Cuba. And over the week we've learned a lot about coding and drones. So right now I'm going to tell y'all about, well, show y'all a little bit about what we've done. Crap, this ain't supposed to happen. Can y'all help?
I can take a look at it.
Yes, please.
Have you checked the propellers?
No, how do you do that?
You just have to look at the angles on the propellers. The different angles work in combination with the direction of the motors to create lift for the drone. If the propellers are in the wrong position, the drone will not have enough lift to get off the ground and will do what you just saw, where it just spins. You should be able to fly it now.
Thank you. This exact scenario played out on our first day of playing with the drones. That's when I learned the meaning of our shirt motto, experiment, fail, learn, repeat, because I was experimenting, playing around with the drone, and I failed by crashing it into a wall, but what's the fun in not doing that? Then I learned from Jeremy that propellers make a difference, and then I repeated it, and it worked beautifully. And
by the way, my name is Jeremy, and I'm from Axton, Maryland.
Hi, my name is Solomon. I'm from Akron, Alabama. I'm going to explain and demonstrate for you a few tricks that we learned. On the second day of camp, we learned to code our drones to do tricks. One trick was to code your drone to perform continuous loops. We also learned to code our drone to do the same trick, but with pauses in between each loop. And I will show you the flips. Sorry, we're having technical difficulties.
Hi, my name is Alexis Frazier and I'm from Tuskegee, Alabama. Today I will be demonstrating you to code a drone to go in a circle. The circle will go right 4 times in a 90-degree angle, and this is my circle. We're having some problems again.
is Dixie and I'm from Andersonville, Tennessee. We learned how to code the drone to do various shapes, including a square. To do so, we had to take the number of degrees in a square, which is 360, and divide it by the total number of angles a square has, which is 4. Since 360 divided by 4 equals 90, we programmed the drone to go forward 2 seconds and turn 90 degrees, repeating 3 more times. This is what the code looks like to us, but this is what the drone sees using JavaScript. If the code is done properly, it should create a square when played.
Hi, my name is Joseph, and I'm from Clemson, South Carolina, and I'm doing the Decagon. As you can see here on the left of the screen is the block form code to make your drone do a dodecagon. And here on the right is the code language called JavaScript. And this is what the drone will see to code the dodecagon. To make your drone do a dodecagon, you first have to find the right angle measurements. To do that, I did 360 divided by 12 because the dodecagon is a 12-sided polygon. My answer was 30. So I wrote in code, move forward 1 second, and then turn 30 degrees to the right. So instead of writing that 12 times, I used a loop. A loop is a code that will repeat the command as many times as you want it to. Since I'm doing a dodecagon, I made it repeat it 12 times. I would show you, but I'm not allowed to hit any of you with a drone.
Hello, I'm Tyler from Waverly, Ohio. The last things we learned about are creating functions or making your own special drone moves and coding a drone to move the way you tell your tablet. First, I'll tell you about the drone moves. Mine is a cool drone move that smashes into the ground at the end. There's the code for it right there.
Sorry.
And I added some sound effects, but the sound isn't working. So, yes. Now about the tablet controller. It's an event-driven program that lets your iPad or tablet control the drone through tilting. There's the code right there. You see whenever you tilt one way, it moves that way for a second. And you just tilt your iPad. You have to set up through pretty much Bluetooth to get it to work. So,
Hi, I'm Emery, and I'm from Grantsville, Maryland. This week, our group talked to several people. The first day we were here, we talked to Chuck Roberts from ORNL, and he told us about UAVs. Then we went to KCRC and talked to Ed Dumas as well as Mike Boobin. Yesterday, we went to ORNL and met their unmanned aerial systems team. They all taught us a lot about drones and what jobs there are that involve drones and coding. We'd like to thank everyone that took the time to talk to us this week.
I don't know how you follow up drones flying, but good luck, forensics group. Our last group is a group who worked in forensics all week, and our master teacher leading them was Marcella St. Ange, along with assistant teacher Casey Bass.
My name is Brad Mary, and this is the forensics group presentation. I am from Radford, VA. We were assigned to find out who left the school at Oak Ridge High School. But before we could ever find out who left the school, first we had to find out what on earth were we going to do. So we went to a local museum, which the museum was called Alcatraz East. When we got there, we thought it was originally going to be about Alcatraz, but instead it was a major crime museum with all sorts of stuff. Some of the most interesting stuff was some of the most famous getaway cars of all time. For example, like O.J. Simpson's white Bronco. Then they contained about every era of crime in America. Then they had a lifelike forensics lab, which was mostly interactive. Actually, the whole entire museum was an interactive playhouse for us. It was amazing and fun for us, and there was tons of games to teach us why would they collect artifacts like this and what were they about. Now then, on to the crime scene review.
Hi, my name is Jinxia Zhang. I'm from North Carolina. I'm also part of the forensics group. To begin the investigation, we had to check out the crime scene. Evidence found at the crime scene was a skull with blood, a note with handwriting, shoe print, hair and fiber, and money. There are 5 women that claimed the skull was theirs. We had interviewed them about their shoe type, pets, pin, and job. Tests that was needed to be performed was chromatography, fingerprinting, skull classification, hair and fiber analyzed, blood typing, and shoe print. I had researched each of the claimants' jobs. Renee Nixon is a veterinarian. Veterinarian, also known as a vet, is an animal physician. They take care of an animal's health. The next claimant is Bailey England. She's a chemist, an expert in chemistry. Helena Thomas is a herpetologist, a person who studies snakes. Zoe Oldham, a zoologist, works with animals. Our last claimant, Alicia Bassett, studies insects. Now, Avon will tell you about the tests we did on the inks using chromatography.
Hello, everybody. I am Avon Fox, and I was in charge of the section on chromatography. Chromatography is the separation of a mixture by passing it through a solution. In the lab, we use samples of ink from the pens and markers the claimants used. We put the bottoms of pieces of paper with a dot of each of the inks that the claimants used in a solution and let it sit overnight so that the colors could fully separate. The next day, we looked at how far the solution traveled up the paper and what colors the inks consisted of. As you can see on the screen with some of them, I think, yeah, like that one. Okay, by doing this, we were able to compare the inks we used in the letter found at the crime scene to each of the claimants' writing utensils. This exposed 2 false claimants, leaving us with 3 potentially true claimants. And now on to Sophie with fingerprinting.
Hi, my name is Sofia Moss, and I'm a freshman at Northern Garrett High School in Garrett County, Maryland. I'm going to give a presentation on fingerprints. Fingerprints are a trace of impressions from ridges in your finger. There are 3 types of fingerprints: loops, whorls, and arches. 60 to 70% of people have fingerprints with loops, 25 to 35% of people have fingerprints with whorls, and 5 to 7% of people have fingerprints with arches. It is an important clue in investigations and crime scenes. Investigators and scientists only need 10% of a fingerprint to identify it. In our group, we did a series of tests to bring the skull to its rightful owner. One of these tests was to look at fingerprints on a note left at the crime scene with the skull. First, we brushed fluorescent powder with a magnetic brush over the note to reveal fingerprints. Next, we looked at the note under an ultraviolet flashlight. Then we took clear tape and placed it on the note, then pulled the fingerprint tape off and placed it on clean paper. After the fingerprint tape was on the clean piece of paper, we used the ultraviolet flashlight again to get a better look at the fingerprints. Lastly, we compared the fingerprints on the note to the possible suspect's fingerprints and were able to narrow it down. Now I will turn it over to Serena for
Hi, my name is Serena Geary, and I am from Cuba Rushford Central School, located in Western New York. I'm currently a freshman. I will be discussing skull identification. While in class, I learned how to identify animals' bones when using a dichotomous key. I began this by using features of the skull. A dichotomous key is a tool that allows the users to determine the identity of their different choices. These keys consist of questions to lead you to the correct answer. In this case, we ID'd the skull, which is a muskrat. Different ways to determine a skull will be if the head points forward is likely a predator, and if the eyes are in front, they most likely have binocular vision. Which adds if the hole in the skull is near the back, the animal will be on all four legs. These are some things I learned at ORAU. Thank you for this opportunity. Next up will be Jeremiah talking to you about hair and fibers.
Hey guys, this is Jeremiah. One of the processes used to find out who owns the skull was identifying hair and fibers left behind at the crime scene. To solve this crime, we had to identify a type of animal hair and a type of fiber. Both of these were found at the crime scene. We viewed both of these under a microscope and compared them with samples of the claimant's clothing and with samples of their pet's hair. The fiber turned out to be cotton from the claimant's clothes. The animal hair turned out to be cat hair. This means that it could have been Zoe, since she's the only claimant that has a cat. Now over to Gracie, who will be talking about blood analysis.
Hello, my name is Gracie Cole. I am from Alabama. This year I will be a freshman in high school. I'm presenting the part of the investigation that is blood typing and unknown substances. The blood evidence we found at the scene of the crime was used to match, find, and identify the correct claimant of the skull. There are 4 blood types, A, B, AB, and O. After testing the blood types of the claimant's blood and comparing it with the type of blood found at the crime scene, we found out that the claimant of the blood of the skull is an O blood type. And also, we performed 6 different tests on 5 different types of substances that were found in the claimant's blood samples. After further testing, we compared and narrowed the list down to 3 claimants. Next, we have Chase presenting shoe prints.
Hello, my name is Chase Bender, and I am a student of Northern High School in Garrett County, Maryland. I am also a part of the Forensic Science Group. I will be talking to you about shoe imprints. In our investigation, we found shoe imprints on the floor of the crime scene. To investigate the shoe imprints, we decided to make casts of the prints. To make the cast, we mixed 2 cups of plaster with 1 cup of water. Then we put it on the print and waited for it to dry. When the cast dried, we took it out of the clay mold and inspected the markings and sizes of the shoes. I found a Nike symbol on the arch of the outer sole of the shoe. This left only Zoe, Bailey, and Helena, since they said that they were wearing Nike that day. After examining all of the evidence, we came to the conclusion that Zoe was the rightful claimant. The interviews, chromatography, blood, fingerprints, and shoe prints all pointed to Zoe being the rightful claimant of the skull. Special thanks to Marcella and Casey for being our amazing teachers this week, and Marla Newport at Tennessee Bureau of Investigations. Finally, thank you from all of us in the ARC ORAU Science Academy to Kayla Canario, Pai Moau, I'm sorry if I pronounce these wrong, Marie Westphal, Jennifer Tyrell, Emily Halilovic, Tim Thomas, and Dr. Thomas Zachariah, and all of the K-12 staff, sponsors, and supporters.
Okay, so that concludes our presentations. We also have an 8th grader who is a student videographer for us. She's not here today, but her name is Sophie Bruce, and she put together a video of our week, and we'll watch that video while the students line up accordingly for the certificate presentations.
To find a problem and solve it. The project is to solve that problem by building something or designing something in the program that we use, which is Tinkercad. And you're supposed to design something and then use that design and 3D print it and what you 3D print is to solve the problem. And the 3D printing group did a trip Wednesday, and we went to 3 Dimensions Design, which is this guy's company that he does with his wife, so it's just him and his wife. And we saw a bunch of different 3D printing machines that he has, and he has 3 different machines in the room that we saw, and they're all different kinds. One is a sand printer, and it's like drywall, and it goes over. And he has just a regular 3D printer, and a upside down 3D printer. And he told us a bunch of things that he showed us a bunch of things that he's printed, and he brought them in, and then we got to call these little dinosaurs that he printed, and we told him what we were printing in the group.
We are using Tinkercad to 3D print designs that we made to help solve problems in everyday life. We take basic shapes and cut them down into our ideas.
Drone group, we are flying drones, testing to see what will work. We're doing obstacle courses, taking some pictures to see what we've done. Like, we're keeping notes on what we've done and what goes wrong so we can fix it. We're also working in coding, which coding is giving the computer instructions for it to complete a task. So we're putting instructions into the code so that the drone will either fly up, rotate, go forward, go back, right, left.
Well, I've learned that drones can be used for medical things like delivering medical supplies and helping other people, which I really didn't know about that. If you fly too high above the ground, you're going to have a pilot's license, which you're going to have to work your way through to get that. And if you enter someone's property, they can shoot you down, which I'm not sure if that's been confirmed, because it just now entered the law.
The shooting yesterday, they were talking about how they programmed their drone. They said they had they had cameras. We had I think one of the cameras was G-Stanex. And I asked them, do they use coding? And they said, yes, they do use coding. But the trip we did this morning, they were showing us how they call the Raspberry Pi as a machine. And they have a map that showed everywhere when they flew their drone. They flew one drone 5 miles from where they were working.
In the forensic science group, we're analyzing a crime scene that we found
there was a skeleton of something that we have to analyze, and there's tons of clues and stuff, and we're all analyzing it. And right now, me and Ava are analyzing the hair follicles and like the fiber and stuff.
We are basically doing a case about a missing skull. We are classifying people through a variety of tests. As a field trip, we went to the Alcatraz Museum. There we did a few projects, I guess, on recovering fingerprints and blood splatter. We also went through the museum and found out the history of crime and all that jazz.
Right now, we are going over blood testing, ontology, fingerprinting. Like, blood testing is how you find out what DNA it is, and we're also going to go over hair samples, which would have, well, hair, you can take a hair sample, it has DNA on it at the ends from the roots. Things that we did at ORNL included seeing the graphite reactor, which was used to help make the atomic bomb.
So, graphite reactor, which is where they were making nuclear bombs during World War II, kind of dropped on Hiroshima and Nagasaki in Japan. And there was a whole lot of research going on there even after the war. Like, Curie, the person that started X-rays, came there and studied for a while.
And then we went and seen some supercomputers, including Summit and Kyne.
Then we went to their facility. They were like a big old supercomputer there called Titan. We learned about like what the supercomputer can do and how it helps people understand things. Like instead of just focusing on like the computer on one problem, like different sections of the computer, focus on different problems so that in the end they can figure it out and find it and make it work.
Then we went and saw the first 3D printed house, Amy.
Yeah, they're in a 3D house they went to. They showed us how they made it, the installation, which was a pretty good idea. Then turned on the stove by accident and it works.
We went to the riverboat, and whenever we got inside it was really classy, and they had a DJ in the back, so he was playing music. We had a 2-course dinner, and then we were able to go upstairs and talk with each other and hang out.
We're at the baseball game. Everyone who walks in sits down, grabs their food. The game starts. After the game, we went to the gift shop. People bought shirts, baseball, and everyone had fun.
Good morning. How are you all? Good? My name is Emma Halilovich, and I'm a program analyst at the Washington, D.C. office. So I really want to start off by giving a special thanks to Kayla. Thank you so much for taking the time to work with the middle school students, and also to the master teachers, too, and the resident teachers. So let's hear a big, if you can say on 3, a big thank you to Kayla and the master teachers. 1, 2, 3. Okay. Perfect. So I'm going to start off with presenting the certificates, and I'm going to go by state. And if we can get Tim on the stage as well. So first we have Alabama, and the first participant from Alabama is Leah Acker. Tristan Carter. Gracie Cole. Alexis Frazier. And Solomon Somerville. Okay, if we can get a picture a little bit further in over here. Next state, Kentucky. We have Austin Grote and Jeremiah Moore. Next, we have Maryland. Chase Bender, Emily Holiday, Ariella Mofaro, Sofia Moss, Jeremy Barango, Next, we have New York, Serena Geary and Justin Peer. Next, North Carolina, Baker Ledford, Samuel Ramirez, Jinxia Sheng, and that concludes North Carolina. Next, we have Ohio, Tyler Mathis and George Ratliff. We have Pennsylvania now, Aiden Fox. So in addition to the Oak Ridge certificate, we have here two representatives from the state of Pennsylvania. We have Jennifer, and Jennifer works for the office at the Department for Community Development, Economic Development in Pennsylvania, and Governor Wolf actually is presenting another certificate to you, Aiden. Yeah. Next, we have South Carolina, Joseph Modine. Next, we have Tennessee, Charlie Collins and Dixie Morris. Next, we have Virginia, Brad Marion, Kiera White, and Lauren Wood. Okay, and now we're going to take a group picture with the middle school students. And if we can get Brooksy, Jennifer, and as well, Jill. No, I'm good, thank you. We're going to have a 10-minute break, so come back at 9:55. So 10 minutes, come back, we're going to reconvene, and then we're going to start with our high school presentations.
guys, if we can get seated, we're going to start in about 2 minutes.
It's a PowerPoint, so it's and then I'll close, you don't want me back anymore. You don't need color safety anymore. So it's the only one out now, and so people don't put it in. I closed it.
It's okay, just look at it. I'll just post it.
I don't have someone. Sorry. Do you want me to open something now?
I'm on that. Like, thank you, so now I'll open up. All right, guys, we're going to get started with the high school presentations. My name is Colt Normal. I am the project lead for the 2018 Math, Science, Technology Institute. I've been involved with this program for 12 years. The previous 11 as a resident teacher. This is my first year as the project lead, so before we get the presentation started, I got a few thank yous. First off, we're going to start with parents. I really appreciate y'all sending your kids here for 2 weeks. I know that's a tough situation. We're so glad that you entrust us with them for 2 weeks and hopefully had a great experience, so thank you all for sending your kids. Obviously, this could not happen without ARC, ORNL, and ORAU, so we appreciate those folks. There are a few ORAU people that I'd like to thank real quick. Miss Marie Westfall's in the front row. She's tremendous and helped us out a ton. Pymura, all the communication is really going through Pymura via email. She's standing in the back. She's hiding from me right now. I was going to try to get her out here, but when you see Py on the way out, please thank her for everything she does. Jennifer Tyrell is watching on the live stream from Aberdeen, Maryland. She's up there preparing for another program that starts Saturday, so everybody that's been here for 2 weeks know how involved Jen Tyrell is, and we want to thank her, even though she's in Aberdeen, Maryland right now. Mentors, we have a lot of mentors here from our groups, both teachers and students, so the mentors dedicate their time in 2 weeks, and we really appreciate that. We have a lot of facilitators in the building, and the facilitators are people that spend a lot of the time with the kids at the lab. Those facilitators just really spend a lot of time and a lot of dedicated time to those kids, and we really appreciate them. At this time, if we can, Lofton, can you go get RTs? We have 4 resident teachers that are with our students around the clock. They are pretty much on the clock from 7 a.m. till 10 p.m. for 14 straight days. Anybody that's been a part of our program knows how important they are. We have printed certificates for them this year, and if I can get them in the building, we're going to get them down here. All right, first up, Mary Sue Kelly Cagle. Next up, we have Bridget Kennedy. from Hartsville, Tennessee, Mr. Billy Lovell. And from Augusta, Georgia, Mr. Melvin Dukes. As you can see, our resident teachers are a huge part of our program, and we really appreciate everything they do. And at this time, we're going to get the presentation started from the Fusion and Materials for Nuclear Systems Division with mentors Bunu Varma, Adam Carroll, and Adam Carroll.
Have you ever wondered how robots navigate their surroundings? No? Well, if you have, this presentation is for you. We used robots to navigate through a maze using two different methods with varying success, but the two methods that we used were infrared and touch sensors.
A hypothesis was made that the infrared sensor would be the most effective for getting through the maze the fastest and the most reliably, as in making it through without failing.
The robot that we used for our experiments was called the BOBOT. BO in BOBOT stands for Board of Education, but it's not the Board of Education that you're all thinking of right now. That would be kind of weird. It's actually a microcontroller made by Parallax in order to educate about microcontroller programming. And if you don't know what a microcontroller is, it's like a small computer that you can program to do things like navigate. Like that's what we did with the BOBOT. And the chassis, which is up there, is just the aluminum body piece of the BOBOT, and it just, everything's on it, and yeah.
All right, so the two sensors we used were a touch sensor and the infrared, and the way the touch sensor worked was there would be two metal pins protruding out, and when they would hit a wall or something, it would knock that pin back into another metal pin, which would break the circuit, and which we would have instructions that we coded for the robot to do, where it would turn left or turn right or back up. And the infrared sensor worked similar, but it used light. So when the light reflected back and it got close enough and into range, it would then act. So there was no contact with any obstacles when the infrared, if it worked properly.
Okay, so this project consists of using infrared touch sensors, and we put it on a board, and we also programmed it to go through a maze, it was the same maze each time, and we timed it using a timing system.
The first graph, which is all the way up there above my head, shows the times of the robots that used the touch sensors. We used two robots to collect the data from, and the first one gave us an average time of 25.8 seconds and a standard deviation time of 3.2 seconds. Standard deviation is a number that is used to tell how far something is from the average, and a high deviation means that it will be farther away from the average while a low is closer to it. And the second robot, its average was a time of 27.5 seconds and a standard deviation of 2.4.
The second graph, which is the bottom one, represents both robots navigating the maze using infrared sensors. The first robot, Bot 1, had a standard average time of 16.5 tenths of a second. The second robot, Bot 2, had a average time of 19.3 tenths of a second. their standard deviation was 0.8 seconds. We will now do a visual representation of what the maze looked like.
Roger will be representing our Bobot. This is the demonstration he's using the sensors. As you can see, he touched. As you can see, he ran into many different obstacles using the touch sensors, and now he will demonstrate using the infrared sensors. That was much faster than having used the touch sensors.
The purpose of the experiment is to test the difference between infrared and touch sensors in efficiency and speed. For the touch sensors, bot 1 has a standard deviation of 3.2 seconds, while bot 2 has a standard deviation of 2.4 seconds. These standard deviations are fairly high, as the data is inconsistent and there is no predictable time the bot will get.
So the touch sensor standard deviation was much higher than it was for the infrared. The infrared standard deviation, both bots 1 and bot 2 had a standard deviation of 0.8, as was mentioned before. And that's really low, and that's really consistent, and honestly, it's quite remarkable, because they're both 0.8, that's real consistent, that's real good, especially compared to the touch sensors, which were in the 3s and the 2s, and so it's a lot better. And the infrared robots were also a lot faster than the touch sensor robots. Actually, 9 seconds faster for bot 1 and 8 seconds faster for bot 2.
All right, so it's easy to identify that our hypothesis was correct and that the infrared sensors navigated the maze very efficiently and faster. And potentially with more time, which I would like to have at this camp because it was a great time, we could test more advanced sensors and possibly get faster times and be even more efficient than the infrared sensors.
So we would all like to thank, but not limited to, Andy Rayfield, Kurt Holmes, Benny Varma, Adam Aaron, Adam Carroll, and Kishia Boyd, and to the organizations of ARC, ORAU, and the Oak Ridge National Lab. It's been a learning experience that will undoubtedly leave a lasting impression on our futures.
I'm Cameron McGriff from Alabama.
I'm Alex Baldwin from Tennessee.
I'm Baxter Hostetter from State College, Pennsylvania.
I'm Mabry Watson from North Carolina.
I'm Tiana Gold from Cleveland, Ohio.
I'm Alyssa Appolito from Columbiana, Ohio.
I'm Roger Dixon from Garrett County.
I'm Andrew Gatesman from Lucinda, Pennsylvania.
Up next, we have from the Computational Science, Engineering, and Communications Divisions with mentors Melissa Allen and Bill Cabbage.
I'm Noelle Beswick from Tennessee.
I'm Carol Williams from Ohio.
I'm Jacob Lord from New York.
I'm Noah Aiken from Garrett County, Maryland. For a number of years now, work has been proceeding in order to bring perfection to the crudely conceived idea of a transmission that does not only supply inverse reactive currents in use of unilateral phase detractors, but is also capable of simultaneously synchronizing cardinal nanograms. Such an instrument is known as the... What?
Whoa. Wait a minute. Does anyone know what he's talking about? Okay, dude, you need to speak so people know what you're saying.
Yeah, no one's going to listen to you if you just spout incomprehensible jargon. You need to tone it down a little bit.
Now you can see from informing people on certain scientific topics, you have to simplify them so people can understand them better.
And that's exactly what we've been doing for the past 2 weeks.
We challenged ourselves by trying to answer the question, in what ways can we improve the principles of climate literacy for high school students?
Climate science literacy is the understanding of your influence on climate and climate on society.
The problem is that in today's American society, the topic of climate change has become a highly polarized political debate. And most of us know not on what to do on climate change, but whether the fact that it actually exists.
It's always the same. You turn on the TV to see a debate equivalent to a boxing match. In one corner, you have a politician or businessman representing the 3% of scientists who believe climate change is not caused by humans.
In the other corner, coming out at 141 pounds and 6 foot, Bill Nye the Science Guy, standing up for the other 97% that do.
Bill, Jacob! What? Bill!
All right. Before we went into the so-called boxing ring, we took the time to learn a little more about climate change science.
We talked with Melissa Allen, an atmospheric scientist who taught us how to use a program called MATLAB, which we took real-life temperatures to show climate change.
We went to a meteorology tower called Met Tower D and were able to see real-time data in temperature, precipitation, and wind speed.
We also had the opportunity to familiarize ourselves with some of the tools used by real atmospheric scientists and meteorologists, such as CO2 detectors and light sensors.
And we looked at a lot, and I mean a lot, of graphs. Here are some of the graphs that we analyzed.
We need to move it in. It's yours.
As you can see by the first graph on the top, this graph is showing people's political views and their views on climate science.
Okay, the second graph shows the CO2 emissions from 1870 and on. The temperatures, it also shows the temperatures associated with the CO2 changes. While the black is our historical data and the colored lines are the projected data for future.
After learning all of this, we began our main objective, to communicate complex ideas in simpler terms. We decided that the best way to do this was to design a brochure that could be easily read by high school students and everyone to show what climate change really is about.
For a person to go from idea to action, the process follows this way. A person is aware of a scientific consensus, whatever that topic may be. Interest in this consensus causes the person to further investigate the topic, thus increasing his or her knowledge. With new knowledge, he or she can accept the consensus and eventually take action. That's what we intend for this brochure to accomplish.
For guidance, we look to an article posted by various government organizations called The Essential Principles of Climate Literacy.
Some of the information coming from the climate literacy document, it comes from certain agencies such as the National Oceanic and Atmospheric Administration, the National Aerospace and Space Association, and also we have the...
Noah, you're being too complicated again.
Anyways, we took each page of the document and we used it and we were able to simplify it down to less than 100 words and put it into our brochure. I believe above is if you look at number 1, that's an example of what we had beforehand. And then, is that the simplified one? Is the principle 2? Right over there is the condensed version. And then here's our whole brochure. We playfully named it, "The Future is Hot."
We considered the original document and its purpose, and from there we deleted, added, and rearranged words to make them easier for anybody to understand.
We hope this brochure will better educate people about climate science in simpler terms so they can understand it better. Thank you. Thank you to our mentors, Bill Cabbage, Melissa Allen, and Ross Tatey. Thank you.
All right, we got a little change in the program here because we have a couple early flyers. So, Young Lose Group, y'all not next. We're gonna give you one break. So just hang on right there. We have up next. We have Materials Science and Technology Division with mentor Mr. Zach Ward.
All right, so I'm Trenton Teague.
I'm Destiny Hughes from Western Pennsylvania.
I'm Ashana Howell from Starkville, Mississippi.
I'm Tyler Wade from Ohio. And we have had the honor, privilege, and pleasure to work with the Thin Films and Nanostructures group at Oak Ridge for the past 2 weeks on developing low-cost, versatile sensors for complex applications. So these sensors are based on the Arduino program board, which is basically a microcontroller, which the robotics group has already explained. You can connect it to any computer through this port right here, and it allows you to program the board to do whatever you need it to do, really. You can control nearly anything off of that board and the breadboard. And the reason we chose to do Arduino for our sensors is because it's versatile and it's easy to use and it's cheap. You can find like knockoffs for about $30 on Amazon that allow you to do everything that the real system does. The first sensor that we made, basically as a demonstration, is the photo light sensor. So the photo light sensor basically runs off of these diodes right here. I don't need the mic, I'm good. These sense light. And what these do, you plug them into the board, and they relay signals to this light right here. I'm not going to demonstrate it because I'm carrying parts. I'll show you all this stuff is. And you're not going to see it because this is a small bulb. But this light right here changes colors based on the amount of light available in the room. You wire it through this battery, connect it right here, and it'll run the circuit all the way through. You use different size resistors. This is a 220. I know it's really hard to see. A little small resistor, hard to see, that allows the current to travel through without busting the battery. And what we decided this one for, since this light can change colors as the ambient light changes colors, it's possible for maybe third world applications where you're trying to style very patient plants. You can see the amount of each wave of light that is coming in a certain area. And there's research going on at UT right now that we heard about in tour that say that red and blue LEDs actually will make plants grow better. So you can use this to detect the red and blue light that's needed. Yeah. Do what? Use the mic, okay. Never mind. So you can use this to detect the red and blue light that's needed to grow the plants.
Okay, so the next sensor that I will be showing you is actually around my neck as we speak. This sensor is called the tilt sensor. This sensor consists of LED lights, wires, the breadboard, and the Arduino board. The battery is here, and as you can see, these are the LED lights, the resistors, the jump wires, and the battery. This sensor could be used for anything, such as inside the house, outside, and much more. It works by plugging in the battery, and the LED lights will come on in a certain pattern. Using this inside your house will be as simple as a simple movement or any such, and it will alert you as soon as possible. As of now, I will now give you a demonstration of this. The black wire goes here. which is really hard to see, sorry. And then the red wire goes here. Now, as I tilt the board, you will see that the lights come on in a very orderly pattern. And as I move the board, they turn off or keep going on in their pattern. Yes, they're staying on now. And they stay on for about a couple seconds, and then afterwards they start right back over. This project was very, thank you. This project was very simple to make. It's very easy. As Trenton said, knock off for like 30 bucks. And it was really fun being able to experiment with this and being able to see how you can make something so small and so interesting out of something this small.
Okay, so up next, this is the light theremin, also known as a screecher, which I'm not going to demonstrate it because it will break your ears. This device is very versatile because it can also be used as a motion sensor. So I'm going to demonstrate how it works. So this is the piezo, and basically from these jumper wires, the electricity goes through, and there's supposed to be this light sensor, because this is very bad, so we just use this. And it displaces the airwaves around it and causes a sound. In a real-world situation, it would be used as an alarm system or anything like that.
So up next, we have the touch sensor to where when you so whenever you touch, like if you touch this, it'll turn the light on. So this touch sensor can then be used for like a sink. If you want to like touch the sink and it'll turn the water on, you can touch it again and turn it off. Anything like that. It's very versatile, pretty easy to make.
So in conclusion on these projects, our sensors we designed weren't for any particular application in mind as of yet, because we really just wanted to demonstrate the versatility. This was an old, what was it, like a radio case or something? You pulled some kind of radio out of it, right? Yeah, this was the mount off of an old radio case, a rubber band, and the starter kit, and it's a functioning belt loop system. Hers is a box that we found laying at the side of the lab and one of the lanyards, and it's a functioning like wearable tilt sensor. So we really wanted to demonstrate that you could use these Arduino boards for nearly any application. And some other ones that we came up with were an interlock doggy door, which would allow you to put a sensor in your dog's collar that unlocks the doggy door when it gets close so that raccoons or snakes or whatever can't sneak into your house. And another that they're working on at the lab right now actually is a turbo pump interlock system. So they have these pumps. They run about $20,000. And these pumps are contained in a vacuum pressurized system, so if the pressure gets too high, it blows out the pump. $20,000 is a lot of money to lose. So why not take a $30 board, make a pressure control system out of it, and save your pump? And in conclusion, these things, fun to play with, easy to use, can be used for nearly anything, and really everybody should try one.
As you can see, we are now at the end of our presentation. We would now like to give our thanks to everyone who made this opportunity possible for us. We've really enjoyed being here, and we would recommend anyone to come again. We would also like to give a special thanks to our mentors, Sam, Dustin, Chiang, Matt, and our main mentor, Zach, who is not able to be here right now, but he is watching. So thank you guys so much for making this possible for us.
All right, up next, we had Miss Senna Lockhart. She's a college freshman. Followed us around for the last 2 weeks to all of our external events. She has taken pictures everywhere we've been, so she put together this little video for everybody to enjoy. Up next, we're going to bring up the Research Accelerator Division, Mr. Young Lou's group.
We are asked to come in from about 8 to 5. Generally, you work 40 hours a week. I work from 8 until 4, but I know some people who work from 9 until 5, all 5 days.
I say fiber, you say optics, fiber, optics, fiber,
Good morning. My name is Nick Craven. I'm from Corinth, Mississippi.
I'm Melissa Yanja. I'm from Quilton, New York.
I'm Riley McDowell, and I'm from Titusville, Pennsylvania.
I'm Autumn Peck, and I'm from New York.
So you might know we're the fiber optics group. So this past 2 weeks, we've been working with an interferometer. Let's get a show of hands. How many of you know what an interferometer is? Guys in the back, yeah. All right. So, So basically, and they study, but more specifically, wave interference. So, basically, we use a Mach-Zehner interferometer, and they study wave interference, and we use this to find the coherence of some waveforms, and also decipher an original waveform from a vibration waveform. So fiber optics, they can be used in hazardous areas with a lot of radiation. They also use it at the SNS, which is the facility we were at the whole week. And also, they built one of these that's like 4 kilometers wide, and they use it to first detect gravity, which is pretty neat. They can also be used to transmit data over long distances. So if you ever wonder how we know how 2 galaxies are 700 light years apart, they use interferometers for that. So this is our setup over here. I'm going to scroll down. So those two pictures in the bottom left, they basically have the same thing, but the one on the top is just easier to understand. So we started off with our laser. That's our light source. It's sent into the fiber circulator. That's sent into the fiber optic sensor, and that's reflected back into the circulator. It goes into this coupler, 1x2 coupler, and that's sent to the waves are split. One of them sent to the fiber delay line, which is what we use to cause some interference. And then the other one goes into the polarization controller, which is just another calibration tool we use, but we didn't really use it that much. So all those are sent back into the 3x3 coupler, and there's more interference involved in there. Those are sent into some circuits, which sends data to the digital oscilloscope, which is what we use to collect all of our data and view the waves. So now I'm going to hand it over to our physicists that know what they're talking about.
I'm Elissa, and I did our first experiment. Do you want to scroll up? And for our first experiment, we did coherence, and we observed interference signals. And we used the fiber delay line, and by tuning that, we found that there are 3 circumstances for interference that occur, 3 conditions, and they are L1 equals L2, L2 minus L1, and L1 minus L2 equal 2S. And S is that gap in the sensor over there, and it has to do with length. So depending on the lengths that the waves travel, different interference occurs. And then for our second experiment, we measured this coherence. And we did this by finding the coherence range. And we did that with a bunch of math that I won't bore you with. We used a lot of Excel sheets and a lot of calculations. But that's the coherence range. And in that coherence range, there's a bunch of waves up and down, up and down, up and down. And counting them would take a long time. So we used math to find out how many there were. And each oscillation or each waveform is one wavelength apart, and by calculating the number of waves and multiplying that number by the wavelength, we found the coherence length. And coherence is a correlation that exists between the different phases in a wave, and it's important because finding different coherence lengths on the same waves means that the phase is not consistent, the phase shift is consistent. And our coherence length ended up being 46.4 plus or minus 2.88 micrometers. And I'll pass it on to Riley.
Hi, I'm Riley. I was told to dumb this down to a 5th grade level, so hopefully it's not like really boring. In this next part of the experiment, we use the interferometer to retrieve an original waveform, a vibration waveform. So obviously we need something vibrating, hence the vibrator attached to the fiber sensor. We just applied voltage to the vibrator, which made the vibration waveform, and then after that, we tuned the fiber delay line to the 2S mentioned. This made it so that we got interference from the reflected waves and also the original waveform, so that way we could determine the vibration waveform. After that, it goes into the 3x3 coupler, and it's split into 3 lines as shown, all phase shifted 120 degrees apart. That's to make sure that we have a full cycle, because 3 shifted 120, it adds up to 360, so that's, yeah. After that, we obviously have up there for the measurements, the retrieved vibration waveforms for different voltages applied, which we were supposed to get a linear representation for what voltage we applied, for what amplitude we would get for the vibration. We got more of a polynomial fit, so I guess that's good. After that, that basically makes it so that you don't have to normalize each of the waves each time, and then use each other to remove the discontinuities within the other ones and a whole bunch of calculus, and that you can just, depending on what voltage you get, apply it to that function and know what amplitude you should have. And I'll pass it off to Autumn Peck.
Hey. Okay, so we used the interferometer to study interference. We went and we found coherence, and we found the original vibration waveform, and we graphed amplitude as a function of voltage.
So now it's time for us to wave goodbye.
I
I'd just like to quickly thank our mentor, Dr. Lou and Dylan Smith, who helped us a great deal on this project. And this was an extremely fantastic opportunity, and I want to thank everyone involved that made this possible. Thank you.
And I want to thank Miss Kayla for being so awesome in middle school that she made me want to come back. And yeah.
All right, if you are a participant from the state of New York, I need you guys to line up over here in order. We got to go ahead and get your picture made. So teacher or student participant from the state of New York, get Mr. Tim Thomas and Emma up here on the stage. We're going to do their certificates and picture, and then we'll keep going with the presentations.
Okay, we're going to start with the presentation of the certificates. For New York, first up we have Christy Garlitz. Jacob Lord. Aaron Mangan. Autumn Peck. Michelle Polcaro. John Swanson. And Alyssa Yonta.
All right, our next presentation is from the Joint Institute for Computational Science. This is Supercomputer with mentor Mr. Bobby Wren, facilitator Jerry Sherrod.
Hi guys, I'm Hannah Little from Virginia.
Hi, I'm Anna Lee from Taylorsville, North Carolina.
I'm Ashley Walker from Spring City, Tennessee. I'm Erin Mangan from Arcade, New York.
I'm Dakota Tiller from Edmonton, Kentucky. I'm Austin Myers from Wheelersburg, Ohio.
I'm Blake McCullough from Williamsburg, Kentucky.
I'm Leah Evans from Tynesta, Pennsylvania, and we are your Super 8 supercomputing group. We did our project on understanding and improving today's supercomputers. The question we asked ourselves at the beginning of these 2 weeks was what we can do to improve them and what happens when a problem arises when supercomputers and the technology in them cannot overcome problems on themselves. So supercomputing technology allows us to connect with one another through social media. You know, technology is a big part of everyone's lives these days. I'm sure everyone in here has a smartphone of some sort. Papa Jerry, I saw you shaking your head, I know. It also allows us to make advancements in medicine, technological growth, and problem solving. This also allows us to break down computers, networking, coding languages, and different types of servers, and also allows us to understand the fundamentals of computers themselves.
Okay, so I'm just going to give you a little background on our project. Supercomputers allow us to do many things. However, for most of us who don't understand the full spectrum of supercomputers, a lot of questions remain. However, one thing does remain the same in any instance. Supercomputers are used to generate medicinal solutions to medical problems, or generate solutions to mathematical equations. Some of the main questions that we had going into this project was, what was a supercomputer, how do they communicate, and how are they advancing in modern day society?
Computers communicate using a system called binary, which instead of using place value charts of 10, such as going from 1 to 10 to 100s like you use in elementary school, it uses 1, 2, 4, 8, 16, and so on. So for instance, if you take the number 37 in decimal, which decimal numbers range from 0 to 9, you would have 00100101 instead of 37. If you add all those numbers together with the place values, it equals the same thing. All right, I'll speak of the materials that helped us complete our project.
Some materials that helped us were the RSA tokens we used, the Cat5 Ethernet cables we used, and also a switch, which is a networking device. I'll start off with the Cat5 cables. We actually made these cables ourselves. In our class, we had to cut this wire. You would pretty much take a little device and it'll cut this jack, it's called a jacket, and then it'll expose these wires on the inside. And then you have to line these wires up in a certain color combination. The color combination we used was the T568B combo, or the color code. And that goes white, orange, orange, white, green, blue, white, blue, green, white, brown, brown. So it's very difficult to be able to get all those wires in this little pin right here. And then after that, you have to make sure you take a crimper, it's called, and then you'll crimp all of these down, and then that's how you get your wires to work. These wires are used in everyday business and homes. If you ever see a blue wire running through the wall, this is most likely an Ethernet cable. This is what we had to connect our computers to the switch, which I'll continue on to say. The switch allowed us to connect our computers to the supercomputer. It allowed us to get on the network of the supercomputer, and then from there we were able to take the RSA tokens and then connect to the supercomputer itself. After connecting to the supercomputer, we were able to run programs and write programs on the supercomputer.
So what exactly is a supercomputer? It's basically a super powerful computer. These machines operate at an extremely rapid speed for mostly scientific and engineering purposes, and it can handle extreme amount of computation and a large amount of databases.
Supercomputers are not without flaw. For example, Summit consumes up to 16 megawatts of power, which would be enough to power a small city. It also produces a lot of heat, and in order for it to work properly, it must be cooled properly. So currently there's a water cooling system that is constantly circulating water. In addition to this water system, there are fans that are set in place, but they have their own problems. They produce sound pollution, which can be damaging to your hearing if you stay in Summit's room for an extended amount of time. And supercomputers are not exactly user-friendly. It took us almost 2 hours just to log in with those RSA tokens.
Some future solutions for the supercomputers would be one way to dispel the heat that's created by the cooling fans, or created by the supercomputer itself, would to be the supercomputers are now powered by electrons, which are what power the supercomputer and what powers most things now. But we can use, in the future, if there was a way to use photons instead of electrons, photons are actually little particles of light that create no heat, and they can move in any direction. So it'll make the supercomputer not only faster, but it'll make it not generate as much heat, little to no heat at that. And then if we get rid of the heat, we can also get rid of the cooling fans, which cause the sound pollution. And if we were able to get rid of the cooling fans, that means the workers would be able to work efficiently and without having to leave the room or wear ear protection every once in a while because they won't have a lot of sound.
Supercomputers allow society to understand the problem and to solve them more effectively. By enhancing supercomputers, they develop better to receive human commands. Upgrading the cooling system and the processing power, it allows the supercomputer to reach the summit of its potential.
How about Jerry told us on our first day this was the size of our brains before we got here. And now that we're on our way home, they're this big. You keep falling.
From all of us at Super 8, we would genuinely like to thank y'all for making this possible for us. And we especially want to thank Oak Ridge National Laboratory, Oak Ridge Associated University, and Appalachian Regional Commission. And Papa Jerry, can you stand up, please? We love you, and thank you so much.
All right, we got 3 early flyers. Alyssa, Autumn, and Jacob, you guys need to head out. Melvin's got your lunch and is going to load you guys up. Up next, from the Computational Science and Engineering Division, with Mr. Dalton Lunga and Mr. Lofton Gerberdine.
Okay, so I have a question for everyone in the audience. Who all likes Chick-fil-A? Yeah?
Do you ever wonder how they choose where to put their locations?
Well, we have a show for the very few of you.
We would like to thank all of you for coming out today to our game show called Who Gets the Chick-fil-A? My name is Shay, your one and only host. Thank you. Thank you. Each contestant I have with me today represents a state that may accept the new Chick-fil-A franchise. So now let's meet our contestants.
Hey y'all, I'm Cole Brown from good old Wilkesboro, North Carolina.
Hey you guys, I'm Megan, visiting you from New York. Not really, but I'm Brad from Maryland, not Baltimore. That little triangle on the end that everyone thinks is West Virginia.
Now that you have met our wonderful contestants, the objective of the game is to allow the contestants to fight for the right to hold the honor of housing a new Chick-fil-A. The contestant will buzz in to answer a question about their represented state. The state that has the most correct answers will win the honor of eating more chicken.
More chicken!
Now, what is the population of your state?
Okay, got your attention. I'm not quite sure of that answer. You want to look it up on our program that we created?
According to the program, the population of North Carolina is about 10 million people.
Well, I guess it's a good thing I know the answer to that question off the top of my head, unlike Colton over here. New York has approximately 8.5 million people.
I would like to phone a friend. The population of Maryland is approximately 6 million people.
Ding, ding, ding. For the population category, the winner is North Carolina. Now, whose state has the most income?
Well, since North Carolina has the most people, I think it's okay to say that we probably have the greatest income. But that's not the question. So let's go with an average yearly household income of about $50,000.
Well, for New York, I should just let Colton know that we make about $51,000 a year per household.
I got y'all beat. We have the average household income of about $69,000 per household.
Okay then, the winner of the income category is Maryland. Now, since the two essential questions have been answered, let's consider one more factor. Does your home county already have a Chick-fil-A?
We don't have a Chick-fil-A, and they're hours away from our home county.
We do have a Chick-fil-A in good old Wilkesboro. I'm just going to let you know that right now. I'm about 10 minutes away from it, And let me tell you, those chicken minis are so good. That's only another one. We can make it 5 minutes from my house.
Well, I guess Colton just thinks he can beat me at everything. I just want to let you know that we should get the Chick-fil-A because I have to travel hours for that luxury.
Okay, well, thank you, contestants, so much for being a part of this game and answering these questions to the best of your ability. Although now, the moment you have all been waiting for, with great consideration, we have chosen, drum roll please, Maryland for the new Chick-fil-A.
So you guys are probably wondering what all of that nonsense was about, but we created a computer program with the help of Dr. Dalton Lunga and Lofton Gerberding. The program is displayed by our poster outside. We highly encourage that you look at it. But essentially what we did is we took the 2010 census, which is a whole lot of data, and we turned it into a computer program so that you guys could understand it.
We use a computer programming language called R, which is used for analyzing statistics by many statistics scientists. It has 3 essential elements to the program: the user interface, where we code what you will see as a user and make it easy to understand. There's also the server, where we put the math and all the logic behind the user interface. And there's the running the app, which is applying the server to the user interface and creating an app.
Okay, well, I'm going to go ahead and show y'all our graphics or our pictures that we have up here. Will you scroll up just a little bit? Yep. So this one right above my head, as she mentioned earlier, you have the user interface, the server, and run the application. So we use the user interface is what you see on an application. That can be all kinds of widgets, all kinds of tools, all of that sort of information. And for the server, that is how the application runs. You can change colors in the server, right? Or in the column widths, like if you want to have multiple columns on the application. And then run the app, it's literally one line of code that just says run. Pull it up, and it runs as a whole program and everything. For our project, scroll up to the top one. The very top one right here. So as we said, our title of our project was Decoding and Depicting Our Nation's Demographics, or DD&D. So for the top picture right here, we have the whole map of the United States. It tells you the total population based off of color. So as the colors get lighter, you have a less population, and as the colors get darker, you have more population, a total population of the state. For the second picture, we chose Tennessee that's where we are, you know. It works, it flows. So it shows you the different population for each county in Tennessee. So as I said earlier, lighter colors mean you have less people, darker colors mean you have more people. And for our bottom picture, we decided to do the average income, so per household. So we chose Arizona, I believe, to depict and show on a graph the averages for every county in Arizona to show the prices that they make per year.
As a group, we created a Shiny R program that made visual interpretation of the data within the 2010 U.S. Census easier. As a result of our efforts, we were able to determine the new location for a theoretical franchise. Programming is an art that comes with a need for expertise and precision. RStudio has a built-in messaging system that alerts the user of an impending error. However helpful this may be, the error messages are very hard to interpret for the untrained eye. We had to learn a new approach at comprehending their information, tearing them apart piece by piece. When debugging a program, it is possible to cause a daisy chain effect. To avoid this, only one change should be made at a time. This avoids the possibility of a user forgetting what they had changed, which makes the process even longer. Just as languages humans use to communicate, programming languages have their own grammar and syntax. Programs must be on spot because computers can't work around a simple grammatical error, as humans can when someone misspells a word. At some point while programming, an obstacle will halt progress. While this can become quite frustrating, it is of the utmost importance that you keep working. The feeling you get after overcoming an obstacle can only be described as euphoric. In conclusion, an application was created with the Shiny R application to interpret the census information into visual format. Users of this app will be able to determine the next location of a new Chick-fil-A franchise based upon viewing demographic information. The graphs were created using data extracted from an online source and placing into the Shiny R app for each state's chosen demographics. The users relevant to the project, Carrie Kurlander, Vice President of Chick-fil-A, can use the information displayed to place a new restaurant in the best location according to the qualifications initially set forth.
I also wanted to say, when he said grammatical errors, I know, was it Tuesday of last week, Lofton? I think I'm correct. There was one grammatical error, and we all spent 4 hours sitting there with the same error, and it took one step to fix it. One step. We had Dalton Lunga as our mentor. He came in, he said, oh, I know what it is. You just got to go in here. It was the file name was helpers, and we had saved it twice, so it said helpers, parentheses, 1, close parentheses. He changed it in one thing. So for 4 hours, we just sat there, and he came in 2 seconds, was like, there you go. Works fine. Great, 4 hours gone. That's good. So anyways, I wanted to point that out. So it's very, very complicated. But again, I want to say thank you to everyone who made this possible, especially Lofton Gerberding up there, and Dr. Lunga. He got his PhD, just to let you know. He deserves it. And everyone who made this possible for us. I mean, it was absolutely mind-blowing experience, something that we will never forget. And I want to thank people from the Oak Ridge National Laboratory. I want to thank the ORAU. I want to thank Billy, Mary Sue, Melvin, and Bridget for putting up with us, because I know that was a handful. And to finish off, I just want to say, once again, I'm Colton Bryan from Wilkesboro, North Carolina.
I'm Mariah Bolden from Garrett County, Maryland.
I'm Megan Adolph from Ashe County, North Carolina. I also want to throw in something really cool. Dr. Lunga, will you stand up? He named his personal supercomputer after the 4 of us. Give him a round of applause, everybody.
My name is Shay Snyder, and I'm from Bluff City, Tennessee. It was truly an honor to work with Lofton and Dalton. I will never forget this. And Dalton is a low-key genius.
Your face.
Sorry about that. All right, our last student group is from the Materials Science and Technology Division with mentor Paran Joshi.
Hello, everybody. My name is Mercedes Snyder, and I'm from Pennsylvania.
My name is Zach Reynolds, and I'm from Alabama.
I'm same age from Ohio.
I'm Sierra Manross, and I'm from Pennsylvania.
Now, for the past 2 weeks, we've been working on printing out these tiny little circuits on printers that probably cost more than your house. Well, I say probably, but I mean they're $400,000. So if your house costs $400,000 or more than that, then please share the wealth. I'm going to be going to college. Tuition is pretty pricey, so trust me, I'll use it. Now, that was a funny little example to show you that we aren't working with average day-to-day printers. No, these are advanced printers. And you know what? For advanced printers, you can't just use plastic. Nope. You have to use silver ink. Now, you might be wondering, Mercedes, why did you specify that you're using silver ink? Well, I am more than glad to tell you. Silver is highly conductive, which is very useful in making circuits. And Zach is about to tell you more about circuits.
We use a silver ink Mercedes mentioned in a special printer called an aerosol jet printer. These printers use gas pressure to spray the ink in lines as small as 10 micrometers. Just for a reference point, a single strand of hair is about 100 micrometers in size, so it's pretty small. There are a variety of benefits to using a printer to print your circuits. One of the main reasons is that printers use additive manufacturing, which means instead of, like a piece of wood when you chip out a structure, you're going to have scraps and stuff that you didn't use. Additive manufacturing uses only what you need and doesn't waste anything or create any harmful byproducts that are hazardous to the environment, which is a big benefit compared to the previous creations of circuit boards, which have lots of byproducts that are horrible for the environment. Also, printing doesn't require a mold. So, like, say you're making a piece for a rocket ship, you have to create a mold and then fill in the mold with, like, molten metal, and then you don't ever use the mold again. Printing doesn't require a mold, so it saves hours of reworking every time you change the design of that rocket ship part. Along with all this, these expensive printers can print on a variety of surfaces called substrates. Some of them can be flexible, which allows for a myriad of interesting ideas.
That's pretty shocking, Zach. Yeah. Thanks. And Chandler, you failed. Chandler's the guy in the back, the only guy not dressed up, by the way. He was supposed to laugh, and he really didn't. But I find it pretty nice that circuits can become flexible now. And Chandler's embarrassed, so everybody look at him again, please. All right. But on this current, also electrical, and Chandler, you failed twice. But on this current plane of technology, we can use a lot of different things to print out electrical circuits that actually work, and we would show you, but this video wouldn't work, so just ignore that I ever said anything. But we can use like papers and polymers and cloth, actually, like your clothes, to print electrical circuits on that can be used for all kinds of stuff, like your phone. Everybody but what's his name over here has a phone in here. So that's pretty nice. And to be more specific, we printed a lot of stuff on a polymer called Kapton. And you can do different things with different materials, of course. Like our Kapton can withstand almost 300 degrees Celsius heat. So it can be used in stuff that gets pretty hot. It wasn't a joke, but thanks for snickering somebody. And it makes it really good for curing, makes it time sensitive. And curing is a process that heats stuff up and it removes all the gaps from the silver, so it makes it really conductive. And that really helps in our research. It makes our measurements more accurate, and I'm going to turn this over to Sierra now.
Okay, now to start way back at the beginning of our 2-week journey, or whatever you want to call it. We started with the basics. So we started by printing out 3 different sets of lines using our silver ink on the Kapton, and we used those to measure different length, depth, or we used those to measure different resistances with length, width, and depth. So, as you can see, it caused the graph, like as we added more, it usually caused it
the resistance to go down. And anyway, so the test that we performed helped us to determine how to print our own electrical circuit, and this information was also used to determine how long the LED light that we placed on our circuit above, how long it would stay on and how long it would stay off in a blinking pattern. Once we had actually printed our circuits themselves, then we used a special double-sided electrical tape to connect all the other capacitors and components needed to make our circuit functionable.
We would just like to say thank you to everyone that we met at this camp, especially our mentors, Dr. Joshi and his assistants, Young Chow and Chandler. So just so you know, we weren't just making fun of some random person in the audience. We knew him. Both of them, but we just picked on Chandler. And we would just like to say thank you to everyone who gave us this wonderful opportunity to be here. We really do appreciate it. Thank you.
Okay, up next we have our teacher participants with our first presentation coming from the ORAU Cytogenetic Biodosimetry Lab, Dr. Balaji.
Golly gee, Miss J, what are those blue things right there?
Well, Ashley, those blue things are chromosomes.
What's so special about them?
Ashley, chromosomes carry your cell's genetic information.
What makes up a chromosome?
Let me show you the important parts. Do you see those blue dots right there? Those are telomeres. Those are found at the ends of your chromosomes. Agree, that's what I call them. Blue? And do you see those red bars in the middle? Those are centromeres. Those hold the sister chromatids together.
Well, I've heard of mutations before. How do they get there?
Well, the most common way for a mutation to be caused is by radiation exposure.
Gee whiz, what's that?
Let me show you how it works. Michael?
Well, that's pretty nifty.
But wait, there's more. Do you see this part of the chromosome that got knocked off? Well, sometimes it attaches to another chromosome. And now you'll see this chromosome has 2 centromeres. That's called a dicentric chromosome. And the more dicentric chromosomes a cell has, the more radiation it's been exposed to.
Well, that's just amazing. Thank you, Mrs. J.
You're welcome, Ashley. Now run along and have a great summer.
I know that lovely hand there was for our amazing Ashley Wheeler, the sweetest kid in Tennessee. She actually just found out she was doing that after Jacob had to leave. So another round of applause. I'm Christy Garlitz from the lovely central New York town of Afton, New York. And we just got to spend 2 weeks in Dr. Balaji's laboratory, the Cytogenetics Biodosimetry Lab. And we got to spend a lot of time with his wonderful assistants, Terry Ryan, Maria Escalona, and Tammy Smith. So the background of what we did is that dicentric chromosomes, now that you know what they are the gold standard for measuring radiation exposure in lymphocytes. And usually we can measure from 0 to 5 gray of radiation exposure, and 5 gray is already pretty high. It's pretty serious. But the more radiation exposure, the less cells you have to study, and so that was the problem. Can we study higher radiation doses? How can we do that? And so the question was, will this particular chemical, colliculin A, give us more cells to study?
Well, good morning. My name is Michael Adam from Starkville, Mississippi, and I'm a biology teacher. Prior to us arriving here at Oak Ridge, blood was obtained from 2 donors and irradiated at the University of Tennessee in Knoxville. When we got here, we cultured the blood and treated it with colliculin A. And what that did was that causes our chromosomes in the lymphocytes to condense prematurely, much earlier than they would in the normal cell cycle. And that allowed us to overcome the problem of early cell death due to high radiation doses. So then we, hold on guys, sorry. We got our chromosomes in our lymphocytes and we put them on the slide and we applied the fish technique. And with the fish technique, we applied different region-specific region-specific probes with different dyes on them so that we could see the different regions of the chromosome. And then we gathered images and analyzed them using Metaphor.
Thank you, Michael. I'm Michelle Polcaro. I live in Binghamton, New York, and I teach with Mrs. Garlitz at Afton Central School. The results that we gathered was that colliculin A did allow us to observe a sufficient number of cells, and it showed a similar trend in chromosomal aberrations or changes. We called them mutations earlier. It's not the same thing. Per cell as the traditional method. So we noticed that there continued to be, as radiation increased, the aberrations per cell also increased. And up here we have a sample cell which was exposed to 20 gray radiation, which is an extremely high dose of radiation. And you can see that long blue and pink thing right there is actually a septocentric chromosome, which means that there are 7 centromeres on it, which was something that nobody had actually seen before. So it was very cool to see.
I'm Christy Hall from the great state of Wilkes County, North Carolina. State of Wilkes County. And I teach biology honors and earth environmental science honors. At the conclusion of the data that we collected using this new chemical, we were able to realize that yes, this colliculin A does yield an adequate number of chromosomes that can be studied at a much higher dosage of radiation. So we were successful in doing that. Now the lab that we worked with, we have one member here with us today, Ms. Terry, if you'll take a stand please and let us, or raise your hand and stand up. There you go. Yes, yes. She and her colleagues will actually be going to the next step and looking at doses even higher than 20 gray. So that's the next part. So we were very excited to be a part of this process and to do something new that nobody had ever done before and collect some data and start that ball rolling. So we would also like to thank all of the mentors that we had. We'd like to thank the doctors and the professors that we had here, and we'd like to thank the students. The students made this experience very, very enjoyable, and we had a really great time, and we'd like to thank all the organizations that contributed and helped us to be able to be here, because I've had a wonderful experience, so have my colleagues, and we wouldn't have been able to do something like this without you. Thank you.
Okay, up next, from the Chemical Science Division, ORNL, and Dr. Barbara Evans' group.
I'm Mary Coulter, and I'm from Tennessee.
I'm John Fisher, and I'm from Ohio.
Hi, I'm Barbie Vina. I'm from Pennsylvania.
Hi, I'm Christina Rogers, also from Pennsylvania, and we wanted to start you off with a little...
We are insane!
Okay, all right. There's always one, right? That wasn't too bad. I think we could have done better. But if you're from Pennsylvania, one of your favorite things is the Penn State Nittany Lions, and our research is also dealing with one of your favorite things. It allows you to use your smartphones, which I see some of you using right now. Parents are the worst, you know? So it also allows you to use your iPads, your laptops, your television. It allows us to travel places by planes, trains, automobiles, big yellow school buses, or the minivan if you get there fast enough. And it also allows us to have electricity in this room and to be in a nice climate right now and be nice and relaxed, not too hot and not too cold. And so what I'm getting at is energy. All of these things require energy. And we know that our energy resources are limited. We have non-renewable resources like fossil fuels that aren't going to last a lifetime. And we love energy. We would be probably a mess without it. So our big picture is to really look for the energy sources that are going to be sustainable for our future energy needs and clean energy and just provide for us. So that's our big overall question.
Did you know that there is free energy all around us? All we have to do is harness it or harvest it. Solar cells harness sun's energy, and hydroelectric dams harness the river's energy. These accomplishments were advancements of their time, but now is our time. It is our time to create advancements in biofuels. Biofuels, as opposed to fossil fuels, like Christina told us, like coal or oil, is made from biomass, which is a plant material. Biomass is abundantly grown and easily harvested. Plants are the future of energy. Scientists have been exploring biomass for some time now. For this presentation, we will study switchgrass. Switchgrass is a tall grass that grows very fast. Several reasons why we study switchgrass is because it is a perennial, means it'll grow over and over again. It'll only be planted once, and you can harvest it several times. It is easily grown in places where not many things would grow, like on a rocky hillside or poor soil conditions. It's non-invasive, so it'll grow just where we plant it and typically not places where we don't want it to grow. It's harvested like hay, so farmers already have the equipment to harvest this and store it, bale it, and ship it to places where they can process it. Turning switchgrass into biofuel is still in its infancy, but there's much to learn on how to break down the cell walls of the plants, the cellulose and lignin, into ethanol or into sugars, and then eventually into ethanol.
Let's try that again. We can't let Pennsylvania beat us. OH! That's a little weak, but that's all right. Anyway, she's right. Well, we've been hearing about biofuels for decades. And before we can really realize the potential of biofuels, we really need a much more comprehensive understanding of just exactly how the source plants are organized at the molecular level. And that's where heavy water that you guys create right here at Oak Ridge comes into play. Now, personally, I have to admit, I didn't really understand all the uses for heavy water. I thought it was just sort of a byproduct of nuclear power. But as it turns out, heavy water has been used extensively to help to understand the intricate structures that are inside of plant cells. So heavy water's nothing special just beyond the fact that the normal hydrogen in the water molecules have been replaced with an isotopic form of hydrogen called deuterium, and sometimes that's called deuterated water or just simply D2O. It's got some interesting properties. The part that we were more concerned with was the fact that it's really easily incorporated into the plant structure. And once it gets incorporated into the plant structure, other scientists can then bombard those structures with neutrons and look at the scattering patterns, and then you can get a much more profound understanding of all the different details within the plant cells themselves. So one of the things that we had, scientists have had problems with over historically is the fact that a lot of plants don't really like growing in concentrations of D2O above about 30%. And so that limits things for the future potentials. Now, So ultimately, what we were involved with was just in techniques involved with growing plants in better circumstances and understanding just how best to propagate them, how to maintain them right, and how to get them to increase their uptake of this heavy water. If we're going to study these plants in some detail and in a wide manner, we're going to have a lot of these plants, and they have to have good controls placed in them. So in regard to biofuels themselves, there's a lot that we have to learn if we're going to ever make these biofuels compete with these dirty forms of fuel that have been traditionally used that are cheaper but are troublesome in terms of the byproducts that they make. As just mentioned, switchgrass could be an important source of that biomass for the reasons that she was giving, but our particular interest lies in something called lignocellulose. Now, that's a complex word because it's a complex material, but it's basically just a composition of some big, long aromatic polymers called lignin and some long fibers of cellulose, and there's the name, lignocellulose. One of the things about lignocellulose is it's not very easily broken down and into simpler molecules like glucose that we can get at and then ferment into alcohol and other biofuels. So the holy grail is being able to break down lignocellulose. And that's what Dr. Evans has been looking at, investigating for a while, is just elucidating the structure of this lignocellulose so that it can be handled more effectively. So this composite molecule is important to the future of biofuels, and this forms about the basic motivation for the research that we were doing here at Oak Ridge. Primarily, what we need to do is grow these plant sources under some very strict conditions. We can't just throw the seeds out into the grass and see what happens. We need to have measured amounts, controlled growth environments, and steady light. And so we were looking at there are really basically three methods that we can study plants in this fashion. You can just germinate the seeds. You can look at the tillers, which are just branches off of the main stems, and see how they grow. Or you can take cuttings off of the nodes, which is where the leaves come out every so often up the stem. So we were looking mainly at the second two versions of that. We didn't really get into the seeds that much. And we're trying to determine the benefits and the detriments for each particular strategy. So our ultimate goal then was to generate plants quickly and efficiently, and to ultimately maybe develop strains that were easier to decompose under conditions and get at that glucose, which is what the goal of everyone is. So that the process of releasing glucose from lignocellulose is called digestion, and that's the ultimate goal of this whole thing. So as we'll be discussing next here, when lignin is not present, like in paper, the glucose just comes out of it very freely. But when lignin is present, like in the forms of switchgrass in that chopped up fibers, then it's a lot slower to come out. And so being able to propagate switchgrass critically or significantly in a lot of quantities is going to allow for a lot of research to begin to bear some fruit. So.
Okay. Even though I've lived in Tennessee my whole life, I'm not a Vols fan, sorry. We're Commodore people. Vanderbilt. What? Okay, I know, right? I'm going to move over here so I can increase some of the graphs. So in order to best study how to propagate these plants, we first had to have plants to study. So we had cuttings taken from an Alamo switchgrass plant. We had 4 sets of tillers and 8 sets of nodes. Everything needs to be sterilized, so we sterilize the fume hood using a 5% bleach solution, and then surface sterilize the nodes and the tiller cuttings. The nodes were then embedded into sterile petri dishes full of agar with a specific growth media, wrapped in parafilm to prevent any contaminants, and then placed under a fluorescent grow lamp. The tillers were placed in jars of another growth media, wrapped in parafilm, and then placed under a halogen lamp, which is actually a little bit, which has a higher intensity. And I don't know how to make this bigger. Okay, never mind. Well, whatever. So the nodes are in the little petri dishes, and then the tillers are in the jars. After a week, oh, thank you. Are you going to show me how to embiggen it? I know it's not a real word. Oh, beautiful. Thank you. Excellent job. Thank you. Okay, so after a week of growth, or allowing our materials to grow. The nodal cuttings did not show very much growth, which was actually to be expected. They do take a lot longer to start to grow and to propagate. But the root cuttings did grow pretty significantly within the week that we had them. However, one of the tillers had a fungus growing on it, so its little plant buddy had to be removed and put into a new sterile jar. Our other study was to look at the difference between pre-treated cellulose and treated cellulose. So the pre-treated cellulose would be the dry switchgrass, and that's this 4 set of Petri dishes right here. The top 2 are the dry switchgrass, and the bottom 2 are paper. That paper has been treated so the cellulose is now freer without the lignin. And by putting some enzymes in and digesting them, we can see that having treated the cellulose, the amount of glucose that was emitted or was released was off the charts. So we compared that to this little baby graph up here of glucose, the amount of glucose versus absorbance. So the amount of glucose that was released from the treated paper is an incredible amount of glucose, and that's what we want. We want that glucose because the glucose can turn into the biofuels. The untreated switchgrass, its absorbance, or the amount of glucose that it had, is somewhere in the middle of this graph, is 0.46. So by treating the cells with some kind of digestive enzyme to remove that lignin, we can get to cellulose easier and then create more glucose that would create more biofuels. And that's ultimately what Dr. Evans's research and her team are working on. So we would like to thank Dr. Evans for opening up her lab to us and letting us work. Yay! It was a lot of fun. And we'd like to thank everybody at ORNL and ARC and ORAU for allowing us this opportunity to come here and play science for a week, 2 weeks. So, all right. Thank you.
All right, up next from the Chemical Science Divisions and mentor Dr. Paranthaman and facilitator Jim Davis.
Hello, my name is Ed Halliburton. I'm from the great state of North Carolina.
I'm John Swanson. I'm from a small town called Cherry Creek in New York.
I am David Scott from Peebles, Ohio. I want to start by saying that we have really enjoyed ourselves this week, or these past 2 weeks. We feel like it was a once-in-a-lifetime experience with working with Dr. Perrons, and we just really enjoyed it. We worked at the Critical Materials Institute, and we worked on high-performance 3D printed magnets. So 3D printing, as you heard some of the middle schoolers say, is an additive manufacturing process, and it allows us to do anything that we can 3D model in a CAD program, we can then make by printing. The really exciting part that we got to work with was that when you add the big area additive manufacturing, which is a really large scale 3D printer, we can not only make small parts, but you can make parts up to the size of a small building. So it's really exciting to get to see that and to work with things that have come up with there. The overall project goal is to reduce the amount of neodymium we use in magnets. So we work with neodymium iron boron magnets, and the reason that we need to reduce that amount that we consume is because we do not have a U.S. Production supply of neodymium. The majority of it comes from China, about 90%. 10% of it comes from some other Southeast Asian countries. So that's led our government to put neodymium on the critical materials list, and that's how it ended up at CMI. So we use magnets every day. You probably don't think about it every day, but probably when you got out of your car, you hit a button for your electric door locks, magnet. So magnets are everywhere, everything from small speakers to large motors to all kinds of things that we use throughout our life. So that's why it's really critical to us to have these magnets. So what we did, we worked with these neodymium iron boron magnets, and our major role, or what we were interested in, was measuring and observing the magnetic flux reduction as we applied heat over time to those. And John's going to tell you a little bit now about how we observed that.
All right. Our research was driven by, as Dave said, we wanted to find what the best combination of magnetic material, compounds, and coatings would result in a magnet that had the greatest resistance to loss of magnetic flux. And to that end, we were each given a 3D printed uncoated magnet that was cut from a larger block, if you will, of magnetic material. They're not very big. You can see they're compared to the size of a pen. This is one of them right here. And so we had to start out by determining what our baseline magnetivity was, and we had to determine what the orientation of the magnetic field was around the magnet, because we had to be able to put the magnet in the instrument that measures the magnetic flux the same way every time. Obviously, we needed to determine the baseline to know where we started from. Now, our magnets had various compositions. That's neodymium iron boron in polyphenol sulfide matrix. The baggie is just an example of the pellets that are melted down and then extruded to make the 3D magnet. The other picture is a magnification of the neodymium in the matrix material. This is the flux meter that we used to determine the baseline and all the other measurements that we made. We took 10 pairs of measurements of each time we used this, and there were 10 pairs because we take a measurement when we put the magnet into the machine, which is the rings. We put it in the middle of that. And then we'd take another measurement when we took it back out again. All those measurements were averaged then, which would result in one data point. Now, to simulate the magnet operating under industrial conditions, next one. We had to anneal the magnets, which just means that they're being heated up. In this case, we heated them to 200 degrees Celsius for a given amount of time, and then it was taken out and allowed to cool. After it was cooled, then we went through the measurement process again using the flux meter, and we did that 3 times, once for 3 hours, once for 23 hours, and once for 69 hours, for a total annealing time of 94 hours. Those data points were then graphed, and that's what we use to do our analysis of the information. I'd also like to mention that part of our experience was being taken on a tour of the manufacturing, excuse me, demonstration facility, where we were able to see the cutting-edge technology that is going on now and being developed, and can make things like this Cobra car. That's a 3D printed car, and that's a part of an engine block that was designed by, excuse me, manufactured by a big area additive manufacturing process. And now Ed will tell you about our results.
All right, so David shared with you a little bit about why we're doing this, because of course we need to reduce the use of the neodymium. And John told you a little bit about our methods, and I want to lead you into our results. So if you will, think about John as being magnet M2, David is M3, and I'm M1. And we'll talk a little bit about some of the things that we experienced and came out of this research. So what we ended up seeing was a relatively high flux loss, and that experience is believed to be due in part to the magnets not having any coating, but it was also due in part to the fact that the magnets did not have, were tested actually at about 50 degrees Celsius above what industry standards are at 200 degrees Celsius. Typically you see about 150. So without having that coating, you had oxidation that occurred, and that increased the flux loss. I'll show you a graph about that. So remember I said that David is M3, he's the big blue line, and I am M1, that's the gray line in the middle, and of course John is M2 there, that's the orange line. So what magnet do you think had the best properties, looking at that? Magnet 2? Okay, because it tracks along more of a linear line, right? If you look at 1 and 3, you see a magnet loss, then you see some increase, and then you see a great deal of loss over time. We didn't have the time that we would like to have had. Volkan, our assistant there that was so gracious with us, I think has had some magnets he's been testing for at least 1,000 hours. So you get a little more data from that. We'll move on here. So some of the conclusions that we drew from our research were that the less than 13% magnetic flux loss that we experienced was within industry standards. We also experienced that at a slightly higher temperature. Industry is usually, as I said, about 150 degrees Celsius. So right now, the Critical Materials Institute is currently they have done this. They are printing a 3D stator that goes to a motor. It's iron silicon. This will be for use in miniature motors. That is centered with bronze, and they'll continue along that line, and I would love to see how that works out, Volkan. So they're continuing to evolve their use of different magnetic powders, different coatings that will optimize the product's performance. So this time I'd like to go ahead and thank those that made this opportunity possible for us. Before I do that, let me just show you a little bit about the stator. So this, of course, is the drawing for that was put in production at the MDF facility. It has been printed there. That's what it looks like. And of course, they're trying to optimize that. I think the goal is actually to create a functional 3D printed motor, electric motor. As far as our acknowledgments, we'd like to thank the support of the Critical Materials Institute, which is an energy innovation hub. It's funded by the United States Department of Energy, the Office of Energy Efficiency and Renewable Energy, Advanced Manufacturing Office. I'd like to thank Mr. Jim Davis, our facilitator, for guiding our research and our product process, and Mr. Volkan Yildirim for his substantial time and effort in coordinating our research and our data analysis. We greatly appreciate the opportunity afforded to us by Oak Ridge National Laboratory, by Oak Ridge Associated Universities, and would like to thank the Appalachian Regional Commission for their substantial contribution to this research and our experience here. We'd like to thank you, Mr. Tim Thomas, and Miss Marie Westfall, and Ms. Emila Halilovich. Let me get that right. Thank you. So thank you once again for all your support. And Mr. Paran's Paranthemum, our mentor. I don't believe he's with us, but we'd like to thank him for his substantial contributions there.
Okay, our final group for today from the Bioscience Division, Dr. Jeremy Smith, with facilitator Mr. Brian Hingerty.
Here comes elastic band, stretching our arms, elastic band, always beyond their need.
Hello, I'm Karen Linkus. I teach at Metcalfe County High School in Edmonton, Kentucky.
I'm Adam Steininger Jr. I teach at Midwest High School in Pennsylvania.
And my name is Raymona Pedigo, and I teach at Jefferson County High School in Dandridge, Tennessee.
You may be wondering what Aquaman, Elastigirl, and Pac-Man have to do with our research project. Well, hopefully by the end of our little talk, you'll see the connection. So let us briefly go over what we've learned these past 2 weeks. Our research project is understanding protein structure using simulations. Proteins are essential for life and the second most abundant substance in the body. They are composed of various combinations of the 20 amino acids and are linked together in chains that vary in length and complexity. There are 4 structure types of proteins. The primary structure describes the order in which the amino acids are linked together to form the protein. The secondary structure is the folding of the protein that gives it the 3D shape, such as alpha helices and beta sheets, as can be seen on our poster. The tertiary structure is the comprehensive 3D structure of the protein. And the quaternary structure is formed by the interaction between multiple chains. The significance of the structure or fold of a protein is directly related to its biological function. For example, keratin is a protein in our hair, and it contains disulfide bonds. People with curlier hair have more disulfide bonds in the keratin than people with straight hair. This is an example of the relationship of the structure to function. Proteins that lack a distinct structure are considered intrinsically disordered and have been linked to diseases such as Alzheimer's.
So during our time here at Oak Ridge National Lab, we use many technological programs to study protein structures. So the first program that we used to study structure was the Protein Data Bank, or PDB. Now, the Protein Data Bank is an open portal where static protein structures are stored. Interesting fact is that in 1976, there were only 13 protein structures stored on this data bank. As of today, there are over 142,000 protein structures stored from researchers all over the world. Now, occasionally, you don't have a protein structure that is in this data bank. So we have to be able to create a protein sequence and come up with a 3-dimensional structure for that. So you're probably now asking yourself, well, how do we do that? There's an open server called the Iterative ITASR, threading, assembly, refinement, which is also known as ITASR. So what that does is you put your protein sequence into the server, and it then looks to see if anybody else has done research on it and can give you a 3D structure. If it can't, It then breaks up that protein sequence into smaller segments and looks for known structures already to give you a 3D representation of your protein. The other program and final program we used to study protein structure was Visualization Molecular Dynamics, or VMD, along with its source code, NAMD, and the analysis tool, QuickMD. Now, the purpose of this was that when proteins fold, they vibrate in that state. So we want to look at the display, the animation, and the analysis of how those proteins fold and then vibrate over the static pictures, which allows us to better understand their function in real life.
We analyzed the simulations that we ran in the QuickMD software in order to study the structure and the molecular dynamics of numerous proteins. By the end of the first week, we were tasked with choosing one of 3 different proteins and going through and running the tools that we were utilizing and come up with the analysis in order to come up with our results. So on the diagram up here, we have several graphs. These happen to be the graphs of our RMSF, which helps to indicate where the proteins are the most flexible. In the one in the upper left-hand corner, that's the myoglobin. That's the one I chose. And it is made up of helical parts and then turns. So where the peaks are in the graph, that represented where the turns were. Whereas the other lower parts were the helical parts of that protein. Then we had the titin, which is, if you look at the diagram that we created with the software, it is primarily beta sheets. So in that graph, there's not a lot of fluctuation happening there that you can observe. The last one over here, ubiquitin, it was a combination of both the helical and the beta sheets, and so you can see a little bit of characteristics of both of the graphs in that one. And the peak at the end is where it can attach in other things. So we worked with a lot of math, but the program utilized a much more complicated version of the math. We isolated it down to this box over here, which is the potential energy, and then we looked at the force, which is the opposite derivative of it. So those of you that one day will take calculus, you'll be working with derivatives, and this is an application of that. So we utilized Excel to produce all of these graphs and also to produce the graphs of our potential energy and force, graphs that are on our poster. Because it was a more simplified model, we used just 2 argon atoms in order to get those graphs. So how do Aquaman, Elastigirl, and Pac-Man relate to what we've done? We decided to look at these in context to something that you could relate to with what we studied. So myoglobin is a protein found in the muscle cells of animals, and it has a strong affinity for oxygen, which allows it to function as an oxygen storage protein, providing oxygen to your working muscles. So diving mammals, such as seals, whales, and possibly even Aquaman, have greater amounts of myoglobin in their muscles, allowing them to remain submerged for longer periods of time.
Again, titin, how does that relate to Elastigirl? Well, titin is the largest protein at over 27,000 residues. Now, our segment that we looked at was only around 102 residues and was comprised mainly of beta sheets. And titin's primary purpose is for the structure and elasticity of muscle fibers. So just as Elastigirl has to retract her arm, Titin would be responsible for the elasticity of your muscle fibers.
Ubiquitin is a small protein that exists in almost all cells in the human body, and it helps to regulate the processes of the other protein in the body. Ubiquitin is involved with the removal process of obsolete proteins. So it is similar to Pac-Man in that the goal of Pac-Man is to remove as many dots as possible. Hopefully this overview gives you an insight to the research we have been able to complete while we were here in Oak Ridge. We would like to acknowledge and thank the above organizations and people, for without them, what we have been able to accomplish during these 2 weeks would not have been possible. We are excited to take back to our classrooms what we have learned. We want to share it with our students and other colleagues, so we want to say thank you to all of you. Thank you.
Okay, at this time, we need students, teacher participants to go ahead and line up as you're supposed to. We'll get the ARC reps up front for certificates and picture.
Pictures, then a group picture of the high school participants, and then high school and middle school students too.
No, just high school. I mean, what is your one group shot of all these people?
We're not doing both middle school and high school. Okay.
And then Maria's going to close.
Okay. Good? You're good?
Okay, let's continue with the presentation of the certificates. We did New York previously, so now we're going to start with Alabama. First one up, Cameron McGriff. Zachary Reynolds for the state of Alabama. Now we have Kentucky, Karen Lucas, Blake McCullough, and Dakota Tiller. Maryland is up next. We have Noah Aiken, Mariah Bolden, and Roger Dixon. And now from Mississippi, we have Michael Adam, Nicholas Craven, Shauna Howell, and that concludes Mississippi. And now we have the great state of North Carolina, Megan Adolph. Colton Bryant, Christy Hall, Ed Halliburton, Anna Lee,
Trenton Teague, Mabry Watson. Now we have Ohio, John Fisher. Tiana Gold. Alyssa Ipolto. James Myers. Paul Scott. Tyler Wade. Kara Williams, Shane Baines, or Bays, and that concludes Ohio. And now we continue with Pennsylvania. If we can get the representatives from Pennsylvania, Jennifer and Jill, on the stage. First up, Leah Evans. Andrew Gietzman. Baxter Hostetler. Destiny Hughes. Sierra Manrose. Riley McDowell. Christina Rogers. Mercedes Snyder. Adam Steininger. And Barbie Vanna. Up next, we have Tennessee, Noel Beswick. Alexander Bauman. Mary Coulter. Ramona Petigo. Shay Snyder. And Ashley Walker. Ashley Walker. Oh, Hannah Little. But she's there. Okay, sorry. Go ahead. We're good. Sorry. And now we have Virginia, Hannah Little. Okay, and now if we can get all the participants, students and teachers for the high school program up on the stage. One final picture.
All the resident teachers, come on down. Mary Sue, Billy, Bridget.
Hey. Good afternoon almost. I would like to invite everyone to join us for lunch in the lobby. Thank you very much for being here. Thank you, ORNL mentors, for your time. Thank you, parents. Hope to see you again soon.